to do is to share my screen, start broadcast. Okay, guys, a very warm welcome to my lesson for today, where we are going to be doing a physical sciences. Okay, I see there we are having some of the information for the next lesson that we had yesterday. So guys, in today's lesson, without any waste of our precious time, we are going to discuss physical sciences. Let me just confirm for the last time. Guys, can you hear me? Can you see on my screen? Is everything okay there on your side?
Yes.
Okay, then it's fine. It's fine. It's fine. It's fine. It's fine. We will just continue, and then everyone else will just find us on the way. So, some of the topics that you're going to be doing in term 3, it's going to include electric circuits. So, I think it might be best for us to start with a very quick introduction, if necessary. It might not be in this same lesson. Maybe at a later stage, we will then go deeper and do some more specialized problems. So just as a revision, allow me to go through these, and then I will give you guys an opportunity to dive in. But for now, let me just quickly do more like a presentation. See, in electric circuits, remember, we've got two types of connections. The first type, which we can refer to as a series connection, and the second type, parallel connection. We did discuss a lot of this just before the May-June exams. But for now, we are going to be going deeper. So let me just very quickly draw an electric circuit there. Remember, this thing is called a cell. The moment I add another one, it is called a battery, with the longer side representing the positive and then the shorter side representing the negative. It's like a cell. Let me just draw a cell there, something of that nature. You obviously have the positive and the negative side. But because on electric circuits, we don't draw the cells that way. We just use a long line and a short line. A long line is the positive, and then the short line is the negative of that type of a cell. So now what I'm drawing is a conducting wire. So this is
Sorry,
where
sir, you're breaking
electrons
up. I'm not sure
travel.
if my network.
Okay. Let me quickly check with Mbali. Mbali, am I breaking on your side? We just want to check if it's on my side or if it's
No, it's fine on my side.
So you were able to hear everything clearly?
Yes.
Okay. Asa, it looks like it's on your side, honorable member. I think what you can try to do is just to leave and then come back. But remember, this is being recorded. I will make sure that as soon as the lesson is done, I post it so that you are able to catch up, especially the parts where you were not able to hear me. But trust me, this intro is what we have done the previous time, but otherwise it's fine. Let me continue for now. So this is a conducting wire, honorable members, where electrons travel or where electricity travel, just for the sake of keeping this simple. So obviously, what we connect on the conducting wire, it's what we call electrical appliances. For example, it could be a TV, it could be a light bulb, it could be a stove, it could be a fridge. Anything that you can think of that uses electricity, it's what we refer to as resistors in electric circuits. For example, we can refer to that as resistor 1, this would be resistor 2, resistor 3, resistor 4. These things in real life are electrical appliances. So you might find that maybe a light bulb, it has got a resistance of 0.5 ohms, a smaller resistance. Maybe a light bulb there, no, that was a light bulb. Let's say this one being a TV, we can just say 1 ohm. And then you've got a stove, obviously it charges or it resists more as compared to others. Maybe we can say we've got a charger there, maybe let's say 0.1 ohm, something of that nature, honorable member. So these are the resistors or electrical appliances connected in series. Remember, the moment you start having, let us say, a switch somewhere there, if we do that, we can say we are having our switch open. So what happens when you connect the things in a series connection is that when you open the switch, everything goes off. Everything goes off all at the same time. And when you close the switch, everything goes on, all at the same time. That's what happens, honorable members, when you connect electrical appliances in a series connection. And then we can have this second type of a connection, which is being called parallel connection. You can have a resistor there, maybe R1, it could be TV, another resistor there, it could be a stove, another resistor there, let's say R3, you can also have another resistor there, which could be R4. In terms of the switches, let me show you something. You can have a switch there, which could be closed or open. I will explain that. You can also have a switch there, so that will therefore be switch number 1. This one can be called switch number 2. You can also have another switch there. It doesn't really matter that much. Let's refer to that as switch 3. So this is what happens, honorable members, or members who are honorable. So you will realize that, let's say switch 1 is closed. If switch 1 is closed, everything is going to operate. When I say everything, I'm referring to R1, R2, R3, and R4, the electrical appliances. Why? Because there is no opening or there is no break of the circuit. When the current flows, it is going to flow through a closed switch. It is able to close. It's like you having to cross through a bridge. If this is a river, water flowing in that direction, and then you've got a road and a road, for you to be able to pass through, you must be having a bridge there so that you are able to pass through. Similarly, with the switch, if the switch is open, electricity cannot flow, but the moment you close, it is able to flow. So that means there is electricity is flowing, it's going to switch R1, it's flowing, there's a T-junction, that means other electricity that side, other electricity that side, and then it joins again, it continues. Can you see? But now, the moment we have switch 2, let's say open, that means there is a break there. We don't have a bridge there. So the electricity cannot be able to go pass through this side, but all of it will therefore pass through that side and then it continues. If you open again switch 3, then it means you've got a, what is it? You've got that switch open. You also have that switch open. So the electricity will not be able to pass through that side or that side. That means everything will then be off. Similarly, when you have switch 1 open, it means electricity cannot have a complete flow. By a complete flow, we simply say the electricity must be able to flow from the positive side without breaking, be able to continuously flow in that direction. But the moment it has to do that, and then there is a break there, already it can't flow. But if that switch is closed, it will be able to flow nicely. If that switch is closed, it will be able to flow nicely. If that switch is open, that means it cannot flow through this side, but it will just continue on this other side. The moment you close this switch, it means now part of the electricity will come through this side. So in which instances do we connect things in parallel? For example, in the house that you are in, you may find that this is the room that you are in, and then your parents or whoever are in the other room. So in the room that you are in, you have switched on the light bulb, but you may find that the light bulb is off in this room. It's because the switch for this room, it is opened, but the switch in the room that you are, you have closed it. When you say close, it's like you switch on. And then the light, what does it do? It glows, yeah. Light bulb close. Yes. That's what happens, honorable members or members who are honorable. A practical example, you see this, what do they call it? I think they call it a multi-plug or yeah, multi-what. I would draw it and then it's going to make sense after I've completed the drawing. You see this thing that has, you can plug there. It also has that kind of a thing where you can plug there, and then you can also plug there. You can also plug there. Again, you can also plug there, and then it has a switch there. I'm sure you know what I'm talking about, honorable members. This, everything here, it's a series connection. Why? Because you can plug something there, plug another thing there, another thing there, another thing there, something else there. The moment you switch off, everything goes off. The moment you switch on, everything goes on all at the same time. This is another type of a series connection. So that was just me explaining the differences between a series and a parallel connection in a more practical way, or maybe the way in which I understood it during my time. I haven't explained more with regard to the calculations or anything related to that. But I've just explained how you can interpret those two. So let me just check if you guys are still there and if you were able to hear all that I've explained. So let's see, guys, did you hear what I've explained up to this point before I go deeper? I hope I wasn't breaking. I hope I wasn't breaking. Bali, did you hear all that I was saying, honorable member? Any questions from your side?
No, there are no questions.
Everything clear?
Yes.
Good. It's fine. I am now going to continue. Okay, so now let's see. Remember, guys, you need to understand all that I've explained in order to be able to understand the calculations involved. Maybe let me introduce to you the formulas that we are going to use. We have got a formula that we normally use to calculate R tot. They can say R tot, R effective, or R resultant. Honorable members, total, effective, or resultant. Simply from the word total, total means you just add everything, you add. everything. So that means you're going to have R1 that you added with R2 that you added with R3 that you added with any other resistors which may be connected in that particular electric circuit. Again, honorable members, I've just explained that we have a type of a connection called a parallel connection. You might need to do some calculations on parallel connections. And when calculating the combined resistance, you use the formula which says, what is it? 1 over R parallel is equals to 1 over R1 that you plus it with 1 over R2 that you plus it with any other resistors which may be connected in parallel. Before I go deeper, let me explain these two formulas to say this one is for calculating R total for the whole circuit. That one is for calculating R parallel. It's in most cases where this part of parallel confuses a lot of you. I'm going to simplify it, honorable members. If you have an electric circuit similar to that, this is what happens. Let's say here we have 1 ohm. Let's say also there you have a 1 ohm. Maybe there you have 2 ohms. And the question says calculate the effective resistance or the total resistance or the resultant resistance. What is the formula for calculating R tot, R effective? I just gave you the formula. The formula is R tot is equals to R1 that you plus it with, R2 that you must plus it with, R3 and other resistors which may exist. So that means, honorable members, in this electric circuit, our R tot, we are having R1, which is connected in series. We will have to plus it with R, not necessarily 2, but R parallel. I'm simply saying we have R in series, we also have R in parallel. For R in series, you can substitute it into the formula. Plus, for R parallel, you have to do a separate calculation. So that means now on the side, you will still need to say 1 over R parallel is equals to 1 over 1. I won't rewrite the formula. You know the formula, again, 1 over R. You remember, Mos, I said the next step, you just say 1 over, all that you do, you rewrite that the same way it is, and then you just say to the exponent -1. Trust me, if you punch that on a calculator, 1 over 1 is 1, plus 1 over 1 is 1, 1 plus 1 is 2, to the exponent negative that, it will give you 0.5 ohms. So now I want to explain what this 0.5 ohms mean. That 0.5 ohms, it simply means you have converted this drawing into this. This is that 2 ohms that was originally connected in series, but what you did was to combine that parallel connection into a single one, which is 0.5 ohm. So can you see now? It means you've got that 2 ohm that you must plus it with 0.5 ohm because it is the one which is the parallel connection. And then that will give you 2.5 ohms. That's how you calculate R effective. So that means, like this formula for calculating a parallel, what it does is to help you to convert this from being parallel to making it a series. That is why I used to say it helps to serialize, the connection from parallel to series, so that we can be able to take that value and substitute it into this formula. So that means if you had another resistor there, you were going to have 2 plus the one for parallel plus that other one. Trust me, honorable members, what makes electric circuits complicated is not understanding this part. It gets worse when we trace the flow of current, but this is the first step that you need to understand. So let me check. Any questions from your side, or are we still on the same page, honorable members, or members who are honorable? Any questions from your side?
No, there are no questions.
But does it make sense, Mbali?
Yes, it does.
Ungasabi. Ungathi uyasaba ukubuza imbuzo Mbali. Ungasabi.
Anginambuzo.
Okay. It's fine, it's fine, it's fine, it's fine. Augustino, I can see you, honorable member. I am well aware that this was more what talk to you. Okay, so now let's see what else can we talk about. There's a lot that we can talk about, honorable members. Remember, all that I'm doing is just coming straight from my head. I haven't got my notes. This is because I want to make sure that I give you guys a feel of what you should know without having to refer to the notes. So now let's discuss something in addition to all that we've already spoken about. Okay. Here's another formula which says V is equals to IR. Where, honorable members, if we have an electric circuit, it could be that, you might be having that, you might be having that, you might be having that. So from what I've learned is that we will be studying a electric circuit with a maximum of 4 external resistors. That means the electric circuit that we will be given, it will be having a maximum of 4 external resistors. So now let's discuss this formula. So you see now, this formula, which says V, it is equals to IR. You use this formula for calculating V. Maybe let me say external. I'll explain some more on that. Could be external, it could be total or for the whole circuit, or V for a particular resistor or for a particular connection. What do I mean by that? When you use this formula of V, it's equals to IR. To know whether you're calculating V tot, it will depend on what you substitute there. The moment you start using that current being for the whole circuit or the unsplitted current, you will therefore be forced to use R tot. The moment you use the current which is connected within a parallel connection, then the R that you're going to use, it has to be for the side where this is connected. Otherwise, if you use an ammeter connected on this side, the current connected there. That means the R that you're going to substitute, it is for that. It therefore means, in this instance where you use, let's say R1, that one is R2, this is, no, A1, A2, A3. The moment you use A1, it means even R you're going to use R taught. A1, you're going to use R taught. The V that you are calculating is for the whole circuit, it's for the total circuit. It is that V for the battery there. But the moment you use A2, the moment you use A2, you see where A2 is connected, it means even what is it, not V, but R there. The R that you're also going to use, it is for that specific resistor. So that means the V, it is just for there. Otherwise, if you use V3, not V3, but I3, ammeter number 3, even the R that you're going to substitute, it is for that side where the A3 is connected. That means the V that you will get, it is for just that. Similarly, there, V, the moment you start using let's say that specific R, the current that is passing through there, it is obviously the same as that one. But what you should know is that because you used a specific R, it means the V, it is just for there. On this information that I've explained, it might not make sense now, but trust me, as we do calculations, that's when it is supposed to make sense. Let me try to explain to you something very much important there so that you have a better understanding. I'm pretty much sure that I won't be explaining this information on our next lesson. I have done a lot of lessons explaining this. On our upcoming lessons, straight away, we are going to be dealing with some more exam type questions. This is how the current flows. Maybe let me connect the ammeter there so that we can read the flow of current. An ammeter can be connected there, ammeter 1. Another one could be connected there, ammeter 2. Another one could be connected there as ammeter number 3. So this is how the current flows, honorable members. This is how the current flows. From the positive side, it goes like that. When it gets there, it splits. Other current will flow through this side. For example, 2 can flow that side, then 2 flows this side. When it gets there, it joins again. It's back to 2 plus 2, which is 4. Continues as 2 plus 2, which is 4, 4, 4, 4, 4, 4, 4. When it gets there, split to that side, joins 4, 4, 4, 4, 4. So that means the current flowing everywhere on series, it is the same. That means it's going to be 4, 4. Even the current passing through that resistor is 4, 4, 4, 4 until it gets there, it splits, then it's 2, 2, and then it joins back to 4, 4, 4, 4, 4, 4, 4, 4. So that means the current passing through there is 4 amperes. That means the current passing through there, it is 4 amperes. But the current passing through there, it is 2 amperes. So on that side, 2 amperes. Also on that side, it is 2 amperes. That is why I was saying, when we say V, it's equals to IR. The moment you use this R, which could be, let's say, 1 ohms, you will substitute the 4 as the current, because current passing through there is 4. But when it comes to R, the moment you start using 1, it means the answer that you get, which is 4 volts, it is 4 volts for specifically that one. But if you used the total resistance there, then the V that you would have calculated, it is that one there. Not an easy one to understand, especially if you are getting this information for the first time today. So now let's see. Guys, any questions up to this point, or are we still together? I'm going to be explaining the last part, and then from there, we will leave it there until our next lesson, when we either continue or go deeper. Any questions on your side, honorable members? No questions. Okay. We're going to assume that there are no questions. Otherwise, if they are there, you will then unmute and ask the question. So now, let me introduce you to something that we're going to be looking into. Something called the EMF, which is equals to, they say, V external. You plus it with V internal. What is the formula for calculating V? What we know is that V is equals to IR. R for external V. What is the formula for calculating V? We just know it's IR. But for internal, we just use small letter r. Guys, the current flowing externally and internally, it is the same. That is why we take it out as a common factor. And then inside there, we remain with capital letter R and small letter r. So you might need to be aware that this is where you will find your internal resistance. You can be having that in parallel, you can be having that. Sometimes inside that battery, you will find that you've got a small R. That's where the internal resistor is. So that means on that formula where you calculate R tot, you need to be aware that there is R tot for external. That can be added with R int. If it's 2 ohms there, let's say 3 ohms there, 1 ohm there, 2 ohm there, you already know how to calculate R external, which is what we started with. R internal, they can just give you and say it's 0.5 ohm. So that means with the knowledge that you have on calculating the R tot, R effective, you just add that with the R int. So that means on that formula, you already have your EMF, which can be equivalent to I into the R external. Let's say it is 2 ohms, then you add it with 0.5. You already have your I, which is equals to 2.5 ohms. Then, if you know the current that is flowing on that circuit, that's what you substitute there. And that's how you calculate your EMF. So the EMF, again, it's like the total amount of electricity for the whole circuit with the presence of R internal. So that means on my next lesson, I'm going to go deeper in explaining the R int, how you can understand or interpret the R int. But how I crammed it in Bali is that if you remember, there are those meter boxes, those are the numbers there. those meter boxes which are connected to the house. And then you have your electric circuit there. You have that. Those are the TVs, light bulbs, and everything. So R1, R2, R3, R4. These are the external resistors. But now, inside that meter box, you remember, Mos, there is that green light. There is yellow, not blue, but green. It's fine. I'll leave it as that. And then there's that yellow one. And then from there, you've got those numbers telling you the units which are remaining. Everything that happens inside this box, honorable members, everything happening inside that box, that's where the R internal is coming from. That's where the R internal is coming from. It's not too much. So that means this box, it also uses electricity to give you the information regarding how much of electricity you've used, how much is remaining. That flashing light, you say electricity is about to finish. It also uses electricity, a small amount of electricity. That's why the resistance, it is so small. And that's why now this formula, it is no longer just V is equals to IR, but it is now EMF. Why? Because we now have this R int. So that means you are having V as a result of external resistors, that you must also plus it with V as a result of internal resistor. Yeah, I think I've tried, honorable members. Trust me, I have tried. One thing for sure, I have explained this many times before. Yeah, I'm not going to ask Augustine because I know that the honorable member has attended many lessons on that and we fully understand. But I'm interested to know if Mbali understands. Mtawelanga Mta, just notice that you joined now. One thing for sure, you've missed a lot of information, honorable member. I will just encourage you to catch up as soon as the lesson is done so that on our next lesson, you will have the questions that you might be having. Now, let me check with Mbali. Mbali, are we okay there before I run away, honorable member?
Yes, I'm okay.
But wait, Mbali, what is it that you can say you have learned in today's lesson? Mbali?
Yes.
Yes, what is it that you can say? This is something that was confusing me, or this is something new that I've learned.
Oh, sorry.
Bring it to Mama.
Oh, I've learned the difference between a series connection and parallel connection. Yes. And how
So
to calculate the formulas.
the R parallel and the R torque.
Yes.
Then it's fine. Just make sure not to miss upcoming lessons when we solve for some exam type of questions. The reason why I'm not asking the other honorable members is because they already know and they fully understand this concept. So that is why you will then see them engaging when we do some more complicated problems. But in your case, because you are attending for the very first time, that is why I'm more interested in knowing if you understand. Okay, so guys, I do thank you very much for joining. Trust me, my name starts with a letter D, and I am out. Shokuthintekile Mbali